Prove the following statements. If n is an integer and n is not a multiple of 5, then n squared has only remainders of 1 or 4 upon dividing by 5. So if we just take it up to the first comma, n is an integer and n is not a multiple of 5, right? So if n is not a multiple of 5, then when you divide n by 5, it will leave a remainder. Right, so that's the first bit. So we need to consider what remainders these could be and then apply them to kind of to the n squared. So if you think about the way division works, right? So if we're dividing something by 5, well, what are possible remainders? So if you think your possible remainders are only 1, 2, 3 or 4. If you leave a remainder of 5, then there's actually no remainder at all. It just means it goes in one more time. If you leave a remainder of 6, well, that means it goes in one more time and the actual remainder is 1. If you leave a remainder of 0, well, that's not anything anyway. So if you're dividing by 5, the only possible remainders you could have are 1, 2, 3 or 4. So if we consider that, as in if we think about dividing n by 5, and then consider, it's only 4 cases, so this is classed as a direct proof by cases. If we can get an expression for n, considering those 4 cases of remainders, then we can square it and have a look at what implications that has on the remainder of dividing n squared by 5. So let's consider the cases for n divided by 5. So consider cases so where n divided by 5 has remainders of 1, 2, 3 or 4, and 4 I guess. So we're going to consider those cases. So if remainder equals 1. If remainder is 1, so that means when we have n, the thing, remember it's dividend over divisor, n over 5 equals the quotient, which would be some k, so that's the amount of whole times 5 goes into n, plus the remainder, which we've been told is 1, over the divisor. Remember, dividend over divisor equals quotient plus remainder over divisor. So if I just multiply all of that by 5, that would say n equals 5k plus 1, right? So if the remainder is 1 when n is divided by 5, n equals 5 times k plus 1 where k is an integer. K must be an integer for that to work. Right, so if we now turn this into an n squared, well, that means if n is 5k plus 1, n squared equals 5k plus 1 squared equals, well, that's 25k squared plus 10k plus 1. So if you look at that, if we pull a 5 out of that, we're looking to show that this leaves the remainder of 1 or 4. So if we can pull a 5 out, so that would be 5 times 5k squared plus 2k, and I'm going to leave the 1 out, plus 1, something like that, right? So that is n squared, right? So that means that n squared can be written as 5 times an integer amount, 5 times an integer plus 1, which means that the remainder is 1. Is 1. So I'm going to, if remainder is 2, so I'm going to skip this bit, I'm just going to go straight, this will be 5k plus 2. The remainder is 2, then n can be written as 5 times an integer plus 2. N equals 5k plus 2 for an integer k. N squared would be, well, it's 5k plus 2 squared, which is 25k squared, plus 10k plus 10k, so that's plus 20k, plus 2 times 2 is 4, so if I pull the 5 out again, equals 5k squared plus 4k, leave the 4 out, plus 4. So this is 5 times integer plus 4. So that means this n squared can be written as 5 times some integer plus 4. So the 5 times an integer bit is clearly a multiple of 5. The plus 4 means that it has remainder of 4 if it was divided by 5. Remainder is 4. So we only need to consider 2 more cases. That's the remainders of 3 or 4. Remember, that's the remainder when n is divided by 5. So if the remainder is 3, so that means that n can be written as some kind 5 times an integer plus 3. N could be written as 5k plus 3 for integer k. Okay, so that would mean that n squared would be 5k plus 3 squared, and that equals 25k squared plus 15k plus 15k, 30k plus 9. Right, now this is a bit awkward because if we do it in the way we've been doing before, as in just take a 5 out of both of those, you end up with a 9, which does, if you think about it, that does imply a remainder of 4, because if you had a remainder of 9, well, it means that 1 extra 5 will go in with 4 left over. But another way you can show it is if I just take an extra line, equals 25k squared plus 30k plus, if I just split this 9 into a 5 and a 4, then we can take a 5 out of this term and we'll still be able to show it's 5 times an integer plus 4. So if we say that's 5, if we say that is 5 times 5k squared plus 6k plus 1, close the bracket, so I've taken a 5 out of all of those, and then we've got the 4. So this is equals 5 times an integer plus 4. So that means the remainder is 4. So we're still on track. And finally, the last case, so if the remainder is 4, as in the remainder when you divide n by 5. So if remainder is 4, is 4, that means n can be written as 5k plus 4 for some integer k, and it means that n squared equals 5k plus 4 squared, which is 25k squared, plus 20k plus 20k, 40k, plus 4 4s are 16. So we now, you're not going to, a remainder of 16, if you think about it, that really means a remainder of 1, because in 16 you get 5 into it 3 times with a remainder of 1. So I'm going to write this as 15 plus 1 equals 25k squared plus 40k plus 15 plus 1, and now I can write that as 5 times 5k squared plus 8k plus 3 plus 1. So that means the remainder is 1. Remainder is 1. So in summary, I've left myself no room at all, but we're trying to show that assuming that it's true that n is not a multiple of 5, then n squared only has remainders of 1 or 4 upon dividing by 5. So we've considered every single case of possible remainders of n, because you can only get remainders of 1, 2, 3 or 4. When you divide n by 5, any other remainder would just be those remainders anyway, or it would be no remainder. So therefore n squared only has remainders of 1 or 4 upon dividing by 5.